Exercise 733 is the type of problem that you would do most often if you were a medicinal chemist or a pharmaceutical chemist, or if you were an entrepreneur. You have a reagent that's really cheap or really easy to get, and you have a product that would be really expensive or that would make a huge impact in the world, save lives. How do you turn the one into the other? That's what this question is trying to train you to do for the very first time in this class. It says identify what reagents you would use to magically transform these things, to start to act as that magician/chef. So in this case, the first thing we want to do is to look at what type of mechanism we have, whether it's SN1 or SN2, because that will let us choose the right nucleophile, strong or weak, and the right solvent, protic or polar aprotic. So in this one, and here, let's just refer back to this little diagram that we made in the previous video, just so we can refer to it. Okay, so we have the leaving group on a primary carbon here. So already we know this mechanism needs to be SN2. You're not going to be able to form a carbocation on that primary carbon, but there's plenty of room for a nucleophile to attack. So we're dealing with an SN2 mechanism. So we want a strong nucleophile. Well, what do we want to add? We want the OH to be there. A strong nucleophile would have an OH with a full negative charge. Now, you can't just have that on a lab shelf. It's very reactive. It would either eat through the container that you have it in, or it would explode. You would want to pair it up with something that would help to stabilize it. So, for example, a positive sodium. And so you could have sodium hydroxide, that as your nucleophile. So that's your strong nucleophile to favor that SN2 mechanism. And then we would just want to pick a polar aprotic solvent. There's a whole bunch to choose from. We could use acetonitrile, HMPA, DMF, DMSO. Let's use DMSO, dimethyl sulfoxide. And that's it. That's all you need. You have sodium hydroxide and dimethyl sulfoxide, and you can make this magic happen. Okay, let's try to do the same thing for this next one. Here, the leaving group is on a tertiary carbon. So instantly we know this is going to be SN1. Okay, well, if it's SN1, we would prefer to use a weak nucleophile. But if that's not an option, that's okay. We could just use a protic solvent. Now, really the best option here would be HBr. That's a good source for the Br, because this H is going to be able to add a hydrogen to that bad leaving group to turn it into a better leaving group. And once that's there, it'll leave, you'll have your carbocation intermediate, and the bromine will be able to attack. But to favor that SN1 reaction, we can use a protic solvent, and no protic solvent is easier to get than water. So that's it. Hydrobromic acid, HBr, and water, and you turn this alcohol into an alkyl halide. Okay, so in this one is fun. So you have the leaving group on a secondary carbon, so immediately we are not exactly sure whether this is going to be an SN1 or an SN2 reaction. But you notice that we have a chiral center. That's why they're giving us this stereochemistry. And notice that the stereochemistry is switched. It's inverted. There's inversion of configuration. You only get that with an SN2 reaction. If it were an SN1, you would get two products, a racemic mixture of both products. So this is going to be SN2. We want to use a strong nucleophile. Just look at the thing you added. That always tells you what nucleophile you need. So in this case, we need SH. But we need it to be a strong nucleophile, so we'll give it a full negative charge. Now you wouldn't want to take that off of your storage shelf. You wouldn't be able to order that molecule from a chemical company like Sigma Aldrich because it's a reactive molecule. You'd want to pair it up with something that would help to stabilize it. It has a negative charge. You could pair it with something that has a positive charge like a sodium ion. So you'd get something like NaSH. So here's your strong nucleophile to favor the SN2 reaction, and then we would just want to use a polar aprotic solvent. There are lots to choose from. I'm going to choose acetonitrile just because it's such a common one, and it's kind of hard to remember. So acetonitrile. So there's our recipe. There's our synthesis. All we need is sodium sulfide and acetonitrile, and we can make this reaction happen. Okay. So in this one, again, fun because our leaving group is on a secondary carbon, so immediately we're not exactly sure whether it's an SN1 or an SN2 reaction, but we have a chiral center, and notice what happens to the chiral center. It inverts, it switches. So the leaving group is going towards us, the nucleophile came in from the opposite direction. That happens in an SN2 mechanism. If it were SN1, we would have two products. We'd have both of the enantiomers. Another molecule where it's exactly the same, but this bond is a solid wedge coming out at us. So that's SN2. So we want to do an SN2 mechanism. Now for an SN2 mechanism, we want a strong nucleophile. Now if you're ever trying to figure out your nucleophile, who knows what that is, right? I mean, it looks like a crazy molecule I've never seen before. But it doesn't matter. Just look at the thing you added, redraw that, and then just put a negative charge on the part that added. That's the nucleophile. Nucleophiles, good nucleophile, strong nucleophile will have a full negative charge. And we want a strong nucleophile because we know it's an SN2 mechanism, because we got that inversion of configuration. Now you wouldn't just want to add that. That's very unstable. You wouldn't be able to find that in a storage container in a laboratory. That'll always be stabilized by some sort of counter ion with the opposite charge. So instead, you could have NaO and then the rest of the molecule. So those are balancing each other out. So there's your strong nucleophile, and then just to help to make sure that that SN2 reaction goes, we would use a polar aprotic solvent. There are a whole bunch to choose from. Let's do HMPA. So if we had this sodium acetate, which is actually pretty easy to make, you just mix vinegar with sodium hydroxide. Sodium acetate and HMPA, we would have the recipe to get this reaction done. For F, we just need to see what type of mechanism it has. The leaving group is on a secondary carbon, so we don't know immediately what it is, but if you look at the stereochemistry, it's inverted. We have a chiral center, and that chiral center is inverted. So this has to be an SN2 mechanism. Well, what nucleophile should we use? You could use this BR, but a good practice would just be to have it as HBr. Now, it might be a little hard to do this SN2 reaction. After all, you have a really bad leaving group. And so this HBr will help to turn that into a better leaving group. This H will protonate this, so you'll get a H2O there, and now it's a better leaving group, and the bromine can come in and attack. Now if you do that, once you create a good leaving group, you might be stuck doing an SN1 reaction, in which case you would still get this. You would just get a mixture of that and the enantiomer, and you just have to purify them. You could do that either with distillation or extraction. There are lots of ways to separate enantiomers. A common way is also with chromatography. If you're taking the lab, these words should sound somewhat familiar. In any event, you do HBr and you can get that reaction done. Because there's some ambiguity about the mechanism, you could probably get this done either way. It definitely would be cleaner as an SN2 mechanism, and if you used a polar aprotic solvent like DMF, but because you have such a bad leaving group, you don't even know if that'll work necessarily. So I wouldn't be strict about whatever solvent you chose here, but you do definitely have to add HBr. For G, For G, there was a typo. If your homework does not have an iodine there, draw an iodine in. So we have that leaving group there, and that's on a primary carbon. So we know this has to be SN2. We're never going to form a primary carbocation, and there's plenty of room for the nucleophile to attack in with this leaving group on this primary carbon. So we want to do an SN2 reaction, but what crazy thing do we need to add as the nucleophile? It doesn't matter if you've never seen what's there before. Just redraw that same exact thing with a negative charge on the atom that attacked on the nucleophile. And we want to stabilize that negative charge. We'll do that with a sodium, and so we'll have NaO. And that's a molecule called sodium ethoxide. It's pretty easy to make. You just take drinking alcohol and you drop some solid sodium in there. I mean, it's kind of dangerous because solid sodium will burst into flames if it hits any water, and almost all alcohol is mixed with water. To some extent, it's very hard to separate the two. So it's a little dangerous, but not too hard to make. So that's our nucleophile, and just to help that's our strong nucleophile. To help that SN2 reaction go, we'll choose a polar aprotic solvent, and so we could use something like, DMSO, dimethyl sulfoxide. And that gets that reaction done. All right, last exercise for chapter 7. We see our leaving group. Our leaving group is on a primary carbon. So we know this has to be an SN1 mechanism. So we want to add a weak nucleophile. We don't want to add just OH-. That's a strong nucleophile. That would favor SN2. We want to add a weak nucleophile like H2O. Remember, oxygen is a weak nucleophile if it doesn't have a full negative charge on it. So we can do that, and you would just have the proton transfer at the very end to get rid of the second oxygen. And then to favor that, you would use a protic solvent. Well, why not just use more H2O? We'll just write H2O once, and that's the whole thing. So easy. All you have to do is dunk this thing in some water, and it turns in to the product you want. So hopefully this was a little exciting. We finally get to be creative. We get to create new compounds using our knowledge of SN2 and SN1 reactions in this exercise 733.